In this collection of slides, what we're going to do is prove the following theorem and its corollary. I will read the theorem and the corollary out loud, but basically the gist and the point of doing this is to prove that splitting fields of polynomials are unique. So the theorem we're going to prove is, suppose that we have two different fields, f1 and f2, and that they're isomorphic via theta, where theta is a field isomorphism. And we're going to assume that we have one polynomial, f1, in the polynomial ring f1 adjoined x, that is irreducible, and another polynomial f2 in f2 adjoined x, which happens to be the image of f1 under theta. That's a little bit of an abusive notation. Theta is technically an isomorphism from f1 to f2, but we can extend that isomorphism really naturally to f1 adjoined x going to f2 adjoined x, and so we are going to abuse notation and call both of those isomorphisms theta. Then what we're going to assume is that E sub I is a field containing f sub I, that E sub I is really just f sub I adjoined alpha I, where alpha I happens to be a root of the polynomial f sub I, and I is going to be in the range from 1 to 2. Then what the theorem is saying is that we can make an isomorphism of fields phi that goes from E1 to E2, and this isomorphism is going to agree with theta on f1, and it's going to carry the root of the polynomial f1 that we've called alpha 1 to the root alpha 2 of the polynomial f2. Now, this is a really important and helpful theorem, but the corollary of this theorem is basically the statement that splitting fields are unique. So the corollary that we're going to prove is a little more general than that. It's suppose that f is a polynomial in f1 adjoined x. It's non-constant. And again, we're going to assume that theta is a field isomorphism from f1 to f2. We're going to assume that E1 is the splitting field for f over f1, and that E2 is the splitting field for the image of f, theta of f, over f2. And what we're going to prove then is that E1 is isomorphic to E2. So we're going to prove it generally if theta maps from f1 to f2, but the real corollary that splitting fields are unique occurs when the field f1 is equal to the field f2, and theta is the identity map. Then if you use that particular instance of the corollary, you get that splitting fields are unique. So now let's go through the proof. First we'll prove the theorem, and then we'll prove the corollary from the theorem. So note that if I happens to be in the range of 1 to 2, then the polynomial, because we're assuming that f1 is irreducible, it follows that f2 is also irreducible, and what we have is that f sub I is equal to a sub I times the minimal polynomial over the field f, capital F sub I of the element alpha I. That reads horribly, but what that's saying is f1, for example, is irreducible. We know that the minimal polynomial of alpha 1 is also over f sub 1 is irreducible, and if these two things are irreducible, then they're just off by a scalar that happens to be in the field. That's all that this is saying, where you're talking about either f1 or f2, and that follows because f sub I is assumed to be irreducible. And what that means is that you have two elements, they're just off by a scalar. That scalar belongs to a field, and so we've seen before when we've been kind of covering these things that this means that they generate the same ideal inside the polynomial ring f sub I adjoined x. So what we're going to use that for is the following. We're going to define a map pi sub I from f sub I adjoined x to E sub I. The map that we saw in the lemmas in the previous slides, that's what pi sub I is. It's the map that evaluates on alpha I. So it sends a polynomial g of x to g evaluated at alpha sub I. And as we saw in the lemma previously, the kernel of this mapping, pi sub I, is the ideal generated by the minimal polynomial of alpha I, and what we've just said is that the ideal that is generated by the minimal polynomial is just equal to the ideal generated by f sub I. As we saw in that lemma that we saw in the previous slide, the map pi sub I is an isomorphism between these between f sub I adjoined x modulo the ideal generated by f sub I and the field E sub I. So pi sub I is a ring homomorphism from fi adjoined x to e sub I, but when we look at that isomorphism modulo the kernel, it becomes, or when we look at that homomorphism modulo the kernel, it becomes an isomorphism. What we're going to use these pi sub I for is to create the map phi. We're going to let the map phi be the composition pi 2 composed with theta composed with the inverse of pi sub 1. Since pi sub 1, when we look at this factor ring, is an isomorphism, we can take its inverse. And a picture here is kind of helpful. It's going to help us understand where we got this definition of phi, and also convince us that it's sort of mapping from the right place to the right place. Right. So pi 1, for instance, takes f1 adjoined x modulo the ideal generated by f1, and it maps it isomorphically to e1. So we want to go backwards. We want to go from e1 to that factor ring. So that's the map pi 1 inverse. It goes from e1 to f1 adjoined x modulo the ideal generated by f1. The map that's a little bit trickier to understand is the map theta. Again, I'm abusing notation here. Theta originally was a map from f1 to f2. We extended it, as I discussed in previously, to a ring isomorphism from f1 adjoined x to f2 adjoined x. What we have to see is that that map theta then again carries over to a map on these factor rings, f1 adjoined x modulo the ideal generated by f1 to f2 adjoined x modulo the ideal generated by f2. The reason that that map carries over to these factor rings is because we've taken f2 to be the image of f1. So we already had the map theta from f1 adjoined x to f2 adjoined x, and it respects these factor rings because theta of f1 is equal to f2. And last but not least, we have this map pi 2 going from f2 adjoined x modulo the ideal generated by f2 to the field e2. And what we want to do is just move sort of linearly from e1 to e2 and let phi be that map. What we have left to do in the proof of the theorem is show that this map phi has the properties that we wanted for the theorem. So the first thing that we have to check is that it maps from e1 to e2. That's what we did on the previous slide. So it really maps from e1 to e2. The next thing we need to do is argue that phi happens to be a field isomorphism. The reason that phi is a field isomorphism is that it is the composition of 3 field isomorphisms. Pi 1 inverse is a field isomorphism. Theta, when we look at it on those factor rings, is a field isomorphism. And pi 2 is a field isomorphism. So something that's a composition of 3 field isomorphisms is a field isomorphism. And the most important thing is we need to see that it takes theta, that it agrees with theta when we look at what's going on f1. So f1 is a field. It's contained in e1, since e1 is just f1 adjoined alpha 1. So let's see what happens when we trace an element A in the field f1 according to this map all the way to f2. So let's suppose that A is an element of f1. Then let's map it via pi 1 inverse back into that factor ring f1 adjoined x modulo the ideal generated by f1. We go backwards, we just take the element A and we look at A plus the ideal generated by f1. That's pi 1 inverse of A. Now when we apply theta to that, going from this first line to the second line, we apply theta in pieces. We apply it to A, and then we also apply it to the ideal generated by f1. So the theta applied to the A is just theta of A as we have written, and theta carries f1 to f2 by hypothesis. So that's why we have the ideal generated by f1 mapping to the ideal generated by f2. Lastly, we apply pi 2 to each of these pieces. Pi 2 again is just take this polynomial and evaluate it at alpha 2, and this polynomial evaluated at alpha 2 vanishes. And so the f2, the ideal generated by f2 part just goes away, and the theta of A part sticks around. And so we see that if we plug A into this giant composition for phi, that what we end up with is just theta of A, which is what we wanted it to do. We wanted phi to agree with theta when we only looked at particular elements of f1. So at this point in time, we have really and truly finished the proof of the theorem. What we want to do on the next slide is show that we have the proof of the corollary so that we can deduce that splitting fields are unique. So now let's go on and prove the corollary. So remember, in the corollary, we're taking a polynomial f. We're no longer assuming that the polynomial f is irreducible. And basically we want to prove not just for one alpha, but that in general that the splitting fields are unique. So let's see. What we're going to do is just a standard induction, and what we're going to induct on is the degree of the polynomial f. So our base case is we're going to assume that the degree of the polynomial is 1. In that case, we're looking at a linear polynomial, and we have seen previously that that means that the root of the polynomial lies in the ground field that we're looking at. And so the splitting field that we're talking about, E1, is just the field F1, and the splitting field of E2 is going to be F2. So when F happens to be linear, then by the assumption of our corollary, we already have an isomorphism from F1 to F2, and that's the isomorphism theta. So in that case, the splitting fields are isomorphic because we are assuming we have an isomorphism. So that's a silly case, that's the base case. So let's suppose that the degree of f is greater than 1. And what we need to do is we need to take p of x to be an irreducible factor of f, because in the corollary we're not assuming that f is irreducible. We want to apply the theorem that we just proved, and the theorem we just proved is only for irreducible polynomials. So f might be irreducible, it might not. Let's just write p for an irreducible factor of f of x. Now let's try and apply the theorem. So let's take alpha 1 to be an element of the splitting fields, to be a root of p of x, and we know that that exists. And similarly, let's let alpha 2 and E2 be a root of the image of this irreducible factor when we look under theta. So theta of p is the image of p, and let's let alpha 2 in E2 be a root of that. By our theorem, what we have is we can find a map, phi, that maps f1 adjoined alpha 1 to f2 adjoined alpha 2, and we want it to agree with theta on f1, and that exists by the theorem that we just proved. Now let's look at some new polynomial rings. Let's look at f1 adjoined alpha 1 adjoined x. So f1 adjoined alpha 1 is the field of coefficients, and then we just tack the x on at the end to work in that polynomial ring. Inside here, alpha 1 is an element of the field f1 adjoined alpha 1, and so we can factor the polynomial f of x as the quantity x minus alpha 1 times something else, times g1 of x. We'll call that the something else, g1 of x. And similarly, if we work in the polynomial ring f2 adjoined alpha 2 adjoined x, we can factor the image of f, and we can factor it as x minus alpha 2, since alpha 2 belongs to f2 adjoined alpha 2, times something else, and we'll call that something else g2 of x. Now at this point I'm glossing over some details that you need to check, but you can check. So let's see here. Since E1 is the splitting field for g1 of x over f1 adjoined alpha, that's something that we need to check, that E1 should be the splitting field for g1 of x. I think the idea is if there was a smaller splitting field for g1 of x, then we would have a smaller splitting field for the whole polynomial f of x, and that would contradict that E1 is the splitting field. So since E1 is the splitting field for g1 of x over f1 adjoined alpha, and similarly E2 is the splitting field for g2 of x over f2 adjoined alpha 2, what we want to do is apply induction. g1 of x is a polynomial. It has degree smaller than f, since we've factored out this term of x minus alpha 1. And we have the map phi now acting as sort of the theta from the corollary, taking g1 to g2. That is something that you need to check. The reason that g1 gets mapped to g2 is because alpha 1 gets mapped to alpha 2 under the map phi. And so the x minus alpha 1 piece of that polynomial is mapping to the x minus alpha 2 of the other piece, and that forces g1 to get mapped to g2 under the map phi. Once all that's established, you can see that we satisfy what we need to satisfy for induction, and induction finishes the result. Right? And that concludes the proof of the corollary and allows us to conclude that splitting fields are unique.